Hello. Today, I'm going to talk about perimeter and area of similar figures, which we've already touched on in sections on, I think, similar triangles and some other similar figures. I think what we looked at were polygons and triangles. And here, they use the word figure because it's not just polygons we're talking about now, it'll be circles also. First off, remember every circle is similar to every other circle. It's kind of simple, really. They have a different radius, so for instance, you take the perimeter and suppose R1 is 3 times R2. Those are the radii of two different circles. Well, then the radius of, the circumference of, say, circle 1, well, that's going to be 2 times pi r. 2 pi r. Well, in this case, R1, that's R for circle C1, that's 3 times R2. Now, for circle 2, which actually has a radius of R2, that's 2 pi R2. Well, we can just pull the 3 out here and write 3 times 2 pi. Well, I hope you guys can write straighter than that. Anyway, 3 times, doggone it, I keep wanting to write r squared. It's 2 pi, and this should be r2. The 2 goes down here, not up here. 3 times 2 pi r2. Well, the radius was 3 times as much, right? And in fact, all the parameters of a circle will work that way as long as they're linear. For instance, a 60-degree arc, which we're going to study arc length in the next section, will have 3 times the length on circle 1 that it will have on circle 2. The area? Well, let's take a look at area. Maybe before we do that, since we looked at the similarity factor or scale factor for circles and realized that that is just the ratio of the radii. In other words, if I put R1 divide through by R2, I get R1 over R2 equals 3. That's in a sense what this says. Our scale factor is 3. What about perimeters? Well, the perimeter of a polygon is just the sum of all the side lengths, right? If they have side length L, I don't know if you saw this in your first algebra class, this is called the sum. And we could write this is L sub I. This is the sum from 1 to m of L sub I. For instance, this is generalized. If this were a square, n would be 4. But, of course, every side in a square is congruent. So this notation would be kind of clumsy for something like that. Suppose we had an irregular quadrilateral. Every side has different length. Then to add side 1, plus side 2, plus side 3, plus side 4. And that's the perimeter. All you do is add up the sides. It's real simple. This is a shorthand notation for that. Well, suppose that, extraneous marks. Suppose that we have two figures and we're going to label their sides L and K. And L sub I equals 3 times K sub I. In other words, for every side in polygon L, the similar figure, polygon K, every side in K is 3 times the size of side L, or L sub I. Well, suppose we add this up this way now. And that's the cool thing about the summation symbol. It works just like any other summation if you actually knew what this number was. So if we write 3 times k sub I, well, what does this mean? This means 3 times k1 plus 3 times k2 on up to whatever n is. It could have 20 sides. K sub n. Well, our distributive law is not confined to adding up 2 numbers or 3 numbers. We can add up any size, any group of numbers we want, as large as we want, as long as they're not infinite. What I'm about to do doesn't work if n is infinity. But as long as you have less than an infinite number of terms, you can write this. So for a perimeter, we could write our scale factor this way, just divide through by k sub I, and write that the scale factor for polygon L versus polygon K, the ratio here is 3. Well, when I compute the perimeter, what do I get? By using the distributive law, we can recognize that this is just 3 times the sum of k sub I. So all we've done is taken our perimeter and multiplied it by 3. And that's what's always going to happen. So if you have a perimeter of, say, L sub I, or let's just say P sub L, for polygon L, which has sides L1, L2, on up to however many sides this polygon has, P sub L will equal 3 times the perimeter of polygon K. That's precisely because of this relationship here. They pretty much go together. Now for areas, this isn't a proof, but it's an easy way to remember it. Suppose we have, say, rectangle A and rectangle B, and any side of rectangle A is, let's use 3 again, what the heck, 3 times B sub I. What's going to happen when we compute the area of this rectangle? Well, we're going to take A1, and if I had, let's say this kind of a rectangle here, and just label them A1, A2, A3, A4, then consecutive sides would also have consecutive indices. So I could write that the area of polygon A was A1 times A2, but each of these is 3 times B sub I. In other words, A1 is 3 times B1. A2 is 3 times B2. So and that's 3 squared times B1, B2. This is the important part. This could just as easily have been written A sub I over B sub I equals 3. So we have a scale factor of 3. Our area has a scale factor of 3 squared. I used a rectangle to demonstrate this because if you ever forget, lay this out and you'll get this. And then remember, it's the same for every figure. If it works for a rectangle, then squaring the scale factor will give you the new area for a triangle, for an irregular dodecahedron, anything you can think of. If you have this scale factor for the 2 figures, then you have this scale factor for the 2 areas. There's no way around it. Well, that's about all we need to know for this section. So this is actually a fairly easy section. You just have to remember that perimeters move just like the scale factor. The perimeter of 1 is either the scale factor times the original, or the scale factor, or the original divided by the scale factor, depending on whether you've got which way you flip these. If you want B1 over A1, then this is 1/3. If it's A1 over B1, then it's 3. So if you're going from the large one to the small one, the scale factor would be 1 over 3 squared. As I say, it's very easy and very easy to remember, so we'll work some problems. That'll help you remember it, and this won't really be a very big section, I don't think. Well, okay, here's a perfect demonstration of what we were just talking about. Similar figures and the ratios of perimeters and areas. In this case, it's areas. And what they want is the ratio of this one here, LM, to FG. We have the two areas. And what is that ratio for the areas? 18 over 24. I think we can reduce that to 3 over 4. 18 divided by 6 is 3, 24 divided by 6 is 4. Okay, our common denominator is 6. That's the ratio of the areas. But remember, the areas are the square of the scale factor. So our scale factor K has to be the square root of 3/4. And we can write that, well, square root of 3, we'll just leave it that way. Square root of 4, we know that's 2. So we got root 3 over 2, or the ratio is root 3 to 2. There we go. All you had to remember was what we just said half a minute ago. I hope your memory is that long. That the ratios of the areas is the square of the ratio of the similar figures. The actual scale factor, you have to square that to find the scale factor for the areas. Or we go backwards. If we know the scale factor for the areas, then we take the square root and get the actual scale factor for the two figures. Or in this case, I think they're triangles. But be sure to notice that we didn't actually need any dimensions for these to figure this out. All we needed was the two areas. Well, here's another one of those. Help me. I don't know who I am or what I'm doing. Now this one isn't really too bad. In fact, it's just like the one we just did. Except, of course, we're going to do it right. What they have here is that the ratios of the areas is 1 to 4. Well, remember, if scale factor is K for polygons, for the area it's K squared. So we can just write that 1 over 4 equals K squared, or K equals 1/2. That would be the square root of 1/4. They used 4 as a scale factor for these two. And inverting this makes perfect sense, because the 1/2 goes from here to here. This is the smaller one. The area of this one is 4 times the area of this. So this side, this person has decided must be 4 times this one. And that's all wrong. It would have to be the square root of that, or 1/2. But remember, we're going the other way. So this wouldn't be 4. This would be 2. And you should get 24 over here. He just misused this as the scale factor. And just don't forget that areas and lengths just don't stack up together exactly the same way. If the length has one ratio, the area is going to have the square of that. Because, well, for one thing, look at the units. The length is always going to be in centimeters, feet, light years, whatever. The area is always going to be centimeters squared, feet squared, inches squared, light years squared. Well, that should be a clue right off the bat. If your units are going to get squared, then it's a real good chance that your scale factor is going to have to be squared also. Well, here's one where they would like us to put our enlargements in order. Which of these actually expands the figure the least? The second, well, let's say, we should go the other way. Which one expands the figure the most? And then the second most, and then I guess you would say the least. Well, let's see here. This one, the side lengths are multiplied by 3. Well, that's automatic. That's what a scale factor means. That's what we do with the scale factor. We multiply each of the sides by 3. We use that fact to derive more information, or theorems, or facts about the perimeters and the areas of these figures whose side lengths have been multiplied by a scale factor, which means our scale factor is, we can just directly write that k equals 3. The perimeter is multiplied by 4. Well, remember, we change the perimeter exactly the same way we change the sides. In other words, if the scale factor for the perimeters, the ratio of one perimeter to the other, is 4, then the scale factor is 4. Here, the area of the original figure, in other words, our scale factor for areas is 5, but that means that k is the square root of 5. Because when we say the scale factor for the areas, what we're saying is k squared equals 5. So k equals the square root of 5. Well, let's see here. The square root of 5 is definitely less than 3. 3 squared is 9. It's like 2 point something. That's less than 3. So this would be the smallest one. If we go from largest to smallest, oh, they want it from smallest to largest. Well, okay, fine. That means this is number 1. The next smallest would be over here. This one would be number 2, and this would be number 3. So this was real easy. In fact, you didn't even have to know what the square root of 5 was. You just have to recognize that the square root of 5 is less than 3. Since 3 squared is 9, we need to square something that's going to come out to be 5. It'll have to be less than 3, won't it? And that's all we needed to know. We don't care if the square root of 5 is 0.7 or 2.9. All that matters is it's less than 3. So that's our smallest. And then second smallest here, and largest right here. Real easy. Now here they're telling us that we need 20 pounds of grass seed to plant grass inside the baseball diamond. That's this one here, the larger one. We have a smaller softball diamond here, and they want to know how many pounds we need for this. We have to assume that we're just laying one thin layer of grass seed on this one and doing the same thing here. In other words, if we put 1/10 of an inch thickness of grass seed over here and 1 inch thick over here, none of our equations would make any sense, because we'd be working with volume, wouldn't we? Right now we only have formulas for area, so we're going to have to assume that we're laying out the seed at exactly the same thickness. Kind of like snow. I mean, how much snow does it take to cover this diamond? Well, it depends on how high the snow is. If the snow is 1/2 inch, that's one answer. If the snow is 1/2 foot, well, that's a different answer. We're going to have to assume that when you're planting grass seed, you just lay out one very thin layer. A layer is consisting of only 1 seed high, I guess you could say. This is 1 seed high, and this one will be 1 seed high. In that case, all we have to do is figure out that we need to know what our K factor is for the area. Well, first, what's K for these two? divide by 10 right off. Yeah. Maybe not. We'll write 60 over 90. And let's divide top and the bottom by 30 and get 2 over 3. That's our scale factor. What we need to know, for instance, we can call this K. But we're talking about area now, so we need K squared. That's 4 over 9. So if I multiply 90, I almost did something dopey. I said 90. Obviously, I meant 20. We got to take our area scale factor for our areas, which is, of course, the original 1 squared. Multiply that by the 20, which makes sense. We've got a 90. We've got a large diamond here and a smaller one here. We have a fraction here, which is less than 1. Well, a ratio that's less than 1, I guess. Probably all fractions are less than 1. Not all ratios are. If this were 9 over 4, that would be greater than 1. But we're going from the large one to the small one. So if we take this one and multiply 4/9 by 20, well, that's 4 times 20 is 80, divided by 9. It's just about 9, isn't it? It's like 8 point something or other. It would round off to 9 for sure. And since we don't have anything with decimal places here, the closest right answer is this one here. Closest right answer is kind of a wrong way to say it. The answer which is closest to the right answer. The actual answer is like 8.88. I don't forget if it goes on repeating or not, or just 8.88. Well, this is the closest one to 8.88, so that's the right answer here, B. All you got to do, once again, just don't forget the scale factor for areas is just the square of the original scale factor. Once you've got that, everything else just drops out as simple arithmetic. Now this is a fantastically designed problem. It's not difficult. But from now until the day you're dead, or you lose your mind and can't read anymore, you will see nonsense perpetrated by people with a point to make. Whether that point is true or not, most of them won't care. They just want you to believe it. And you're going to see nonsense like this literally for the rest of your life. So take a good look at it, and every time somebody tells you something like this, think about where it is they might be messing with you. For instance, in this case, the students read 50 mysteries, but only 25 science fiction books. And I guess this student would like everyone to believe that the students in this study don't like science fiction much at all, and they definitely love mysteries. So he made what this could be called a bar graph. But it's a very misleading, inappropriate, and just plain bad bar graph. The graphics are terrific. That's part of convincing people of things that aren't true. Make it look pretty. That will. Half the people go, wow, it looks so good, it must be true. No. What's wrong with this? There were 50 mysteries, he's got that right here at 50. 25 sci-fi books, he's got that right there at what looks to be 25. So what's wrong? Well, I'll show you. This is closer to what a real bar graph should look like. Notice that the height here is still double this, but the width is the same for each one. This gives the impression that this value, in this case the number of mysteries read, is just double the science fiction books read. Doing it the other way, it looks like it was quadrupled. Maybe it's more obvious if you put them together. Look at this thing. It's huge. It's easily 4 times the size of this. But that's That's fraudulent. The number of mystery books read is not 4 times the science books. It's double. So visually, you can easily be very misleading. As I said, as you go through life, watch out for this kind of nonsense. Unless you're somebody who is fairly crooked and wants to make points all over the place, then definitely do things like this. You can easily mislead people graphically by just appearing to be following the rules. I mean, if anybody called him on it, he could say, well, gee whiz, there were 50 mysteries, and I extended this only up to the 50 mark, and I extended this one only up to the 25 mark. What did I do wrong? Well, you made one twice as wide as the other. That's what you did wrong. You can't do that. That's not fair. You're giving people the impression that this is way bigger than this. This might be larger, but it's not as much larger as this would give the impression. So keep this in mind either way. If you don't want to be duped, always take a hard look at any statistics or graphs that you're given. On the other hand, if you intend to dupe people, well, pay close attention to this. It's a good way to do it. Well, this looks not too bad. First thing they asked us to do is to draw 2 polygons that fit the description that the ratios, the areas are in the ratio of 9 to 6. Well, too bad they said polygons. Circles would be the easiest. But since they didn't specify any particular type of polygon, we might as well grab the easiest one, right? I would say squares would be super easy to draw such that these area ratios were true. Well, here I drew 2 squares, which have the right ratios for the areas. This has an area of 9, 3 squared, and this, of course, is the square root of 6 squared, which is 6. Now, if we have a scale factor of k, then we know that for areas, k squared equals the ratio of the areas. So that's 9 to 6. We have that. So what we need to do is find k. Well, that'll be the square root of 9 over 6. Well, square root of 9 is 3, and this is the square root of 6. That's the scale factor. They asked us about the ratio of the perimeters. But we know now that the ratio of the perimeters is exactly the same as the scale factors. Not for areas. The ratio of the areas is the square of our scale factor. But for perimeters, it's exactly the same. The only thing we haven't done is write this in the simplest radical form. Just remember to make it simple. Well, simplest in this term. I don't know if it's really necessarily easier, but the simplest form always puts the radical up in the numerator. So, for instance, in this case, just multiply the top and the bottom by the square root of 6. And then we get 3 times the square root of 6 over 6. But we can rewrite that as 1/2 times the square root of 6. And that's the way most people like to see radicals written, as some number out here times the radical here. Or root 6 over 2, and that's cool also. Well, you see, this wasn't a really tough problem, and they didn't tell us we had to draw any weird, strange polygons like a irregular dodecahedron or anything. So I just picked the simplest ones. And by now, flipping back and forth between scale factors and ratios of area, ratios of perimeters, that should be pretty easy by now, because you just have to remember that perimeters go up and down just like the scale factor. Areas, well, the scale factor squared. And that's about it.